Hello. Today we're going to look at some waves. So far we've done up as far as heat and things like that and finished with that. So the next section we're looking at is the section on waves. And if we have a quick look at the syllabus, and again remember this is the syllabus and everything we need to know is in here. If you look at what it says here in the syllabus, we have waves as a whole section on page 30 of the syllabus, and the syllabus is linked there online. You can even Google it and read it there carefully to check you've done everything you're supposed to have done when you come to revision in 6th year, whatever. So we have properties of waves, wave phenomena and Doppler effect, and then we go on and we look at sound and waves, and we also look at light and waves later on. So what is a wave, right? So what is a wave? Well, if you take a dictionary or something like that, you will see it says something like this: a wave is a periodic disturbance in a medium or in space. So periodic disturbance, well, something is disturbing a material, or probably most common example. Here we have a tank of water, and we have a tap, and we're going to let the water drop in, and you can try this at home. Get your sink full of water and play. And of course when a drop falls in, we'll see a wave or a ripple spreading out. So there has been a disturbance of the water, and the disturbance spreads out, and it is a regular thing. It's happening regularly here because the input is regular. So it is a periodic, that just means regular, a disturbance. Yep, it's disturbing a medium, in this case some sort of material, in this case water. If we look at it from a side view, this is what we'd expect to see, right? So a wave spreading out because something is disturbing it. So it could be somebody throwing a stone in a pond or whatever. And the medium can be water like this, or it could be air. So for example, when you strike a tuning fork, a disturbance spreads out through the air, and this disturbance is the wave that we can detect with our ears. Light is also a disturbance, but it's a disturbance of electric and magnetic fields that pass through space. And of course that's how your mobile phone signal, your TV signal, your radio signal, and all of that spreads by electromagnetic waves. But again, they all come under waves and they follow the same rules that we are learning here. So what do you need to know? Well, let's just go back again to the syllabus. Properties of waves. Well, we want to look at longitudinal and transverse waves. So what are they? Again, just refer back, of course, to your own book. If we can find it there, here we go. Seems to be page 172 of your own book, introduction, all of that there, and it mentions things like mechanical waves. A mechanical wave is a wave that physically exists in some mechanical thing like water or air or a spring or a string on a guitar or whatever. They are mechanical waves. Something is physically moving. Whereas electromagnetic waves, as I said earlier, are waves in electric and magnetic fields around us. Okay, so that's again all of the definitions as over here. What are mechanical waves, electrical waves, traveling waves, and so on. Let's have a look at a spring. Here we just happen to have a slinky, right? So this slinky here is, it could represent water, it could represent the string on a guitar or whatever. When I hit it, you can see a disturbance spreads up and down along it. You can actually see it disturbing. So that is a wave. A travelling wave is when the wave travels out. So I hit it, it goes up and back. Right? So that's a travelling wave. But a standing wave or stationary wave is, for example, if I set up a regular pattern, right, there's a wave or disturbance, but it doesn't seem to be going anywhere. The centre bit there is up and down. If I can keep it at a constant speed, there we go. Centre bit is up and down, and the end bits are fairly stationary. If I go a bit faster, I might get a different type of wave in there. This is a standing wave, and we'll explain more about those later on. Again, if we go back to our simulations, here's a wave on a string. This again is similar to what's happening with the spring. Here our string is spreading out through a window way off into the distance, so we won't worry about where it ends. So if I just give it one little pulse, hit it, the disturbance spreads down, just like with my spring, right? And there we go. But if we have a fixed end, right, say put it in a clamp, send down the disturbance, it bounces back. There's reflection, right? So waves will reflect, and of course if I were to keep sending out a pulse, they'll begin to meet each other on the way back, and this is what sets up the standing waves that we get, right? Now, so if I oscillate it here, let's see if we can get it, eventually it sets up a standing wave. Again, I can change the frequency and things like that. And these animations and lots more are online. This at phet.colorado. So if you type phet space physics, you get a link to it. There's loads of animations in all areas of physics that you can play with, change the frequencies and things like that, change all sorts of parameters and see what happens. So you can actually do, as it were, virtual physics experiments. So have a look at that site. I'll put a link down below. So there we have a standing wave, right? The wave is, definitely the material is moving, but the same areas tend to be vibrating up and down, and other areas are doing very little vibrations, right? So again, change the frequency and so on. Here, something is causing it to vibrate. It could be a guitar string or whatever, right? So once again, just going back to a pulse, if I hit it, the wave spreads out, bounces back. Spreads out, bounces back. Now in a wave there is no movement of the material. It's displaced up or down, but it doesn't go anywhere, right? It just moves up and down, as in the case of a spring. Which brings us to the next thing we want to just mention. If we go back to the syllabus here, longitudinal and transverse waves. Right, so back at our Slinky, right, longitudinal is this, transverse is this, where we hit the spring and the wave spreads out just like in the animation and the spring moves up and down. That is a transverse wave. A longitudinal wave, if I were to pull the spring together like this, right, I'm not sure if we can see it terribly well there, and just now the spring is vibrating this way, right, and the wave is moving up and back. It's not vibrating up and down this time because I'm pinching the spring together, and you can see the longitudinal vibrations. So let's just explain that a bit more. In a transverse wave first, in a transverse wave, the wave, just like in water on a pond, it spreads out in one direction across the pond. The water vibrates up and down, so it's transverse. Okay? In a longitudinal wave, for example, when I pinched the spring, the wave did go down and reflected back, but the material, the spring, vibrated in and out like that. In other words, the vibration was parallel to the direction of motion, right? So the vibration was parallel to the direction of motion. In the transverse wave, the vibration of the material was perpendicular to the direction of motion. So again, back in the syllabus there, longitudinal and transverse waves, they're important. And again, if we just have a look at your own book there, it's in here somewhere, I'm sure. Okay, there we go. You will see on the next page longitudinal waves and transverse waves. You'll also see the definitions, and again, Leaving Cert exam, it's all about definitions. and being able to do problems and recall stuff. So it's important, and one of the tasks with this, write out all your definitions, draw out the main diagrams of a wave. So it says here, this is he putting on his glasses, the direction of a vibration of a longitudinal wave is parallel to the direction in which the wave is travelling. So that's a longitudinal wave. That's where it's parallel, this one here. Sound waves are longitudinal, right? The transverse wave, the direction of vibration of transverse wave is perpendicular to the direction in which the wave is travelling, right? Waves and water are transverse waves. Also, back in your syllabus, again up here on the top of the page, you will see, if you look at it, there's the thing with the spring, explaining it there as well. And again, you have to read through all of this and have a look at it. You are also asked there on the syllabus, you're asked to, where's it gone now, syllabus back here, discuss frequency, amplitude, wavelength and velocity. Okay, and if you look in your own book, you'll see that nice diagram here shows the main features of wave. The wavelength is the distance from the crest to the next crest, right? Wavelength is crest to crest. Amplitude is how high or how low the material is displaced, right? Normally, imagine again your pond is at rest at this level here, but a wave passes by, pushes it up, and then pulls it down as it goes through. The height it goes up or the depth it drops down is the amplitude. So it's the displacement from the original resting position to the top of the crest or to the bottom of the trough. Again, crest and trough are terms used to describe the highest and lowest point along the wave. The wavelength is the distance from one crest to the next, or in fact from any point on a wave till the next point that's at the same stage. We say that's in phase. So it could be from there to there, because that point there corresponds to this one, i.e. where the wave is beginning downward again. So the wavelength is generally taken as the distance from crest to crest. The frequency is how many waves pass in a second. So if we go back to our little animation here, here's the wave, there's the crest spreading out, there's the trough, right? So it's spreading across there. The frequency, if we increase the frequency in this animation, we can just simply see that the waves come more often. At my cursor there, the waves are passing more rapidly, right? The amplitude is how much, how high they go, and that depends on how much energy is put in. The amplitude of a sound wave is how much energy is in the sound wave. So if I shout at you, it simply causes the air molecules to vibrate more with a bigger amplitude and carry more energy out to you. So that is the introductory bit of waves. There's one formula which we'll look at when we get back and do some mathematics, which relates all of these, where c is the velocity of a wave, f is the frequency, that's how often, and lambda is the symbol given to the wavelength. Well, the velocity, the speed of a wave, is simply the frequency by the wavelength, which makes sense. If the frequency are how many waves pass per second, so if there's 2 waves a second, and each wave is a length, wavelength 1 meter, that means it travels 2 meters in 1 second. So the velocity 2 meters per second. So you just simply multiply the frequency, how many waves per second, by the distance each wave is, its wavelength, and that'll be your velocity. And that formula will be useful there again. Again, the syllabus mentions everyday examples, waves at sea, radio waves, light waves, whatever, seismic waves, earthquakes, things like that. They're waves as well. Okay, so with that, I think we just simply wave goodbye. Thank you. See you next time.